Good morning, dear participant. Good afternoon and good evening. Welcome in this session. And this is the fifth session today of 1 week faculty development program on computing with MATLAB and LaTeX software, indispensable tools for researcher. Hope all are enjoying these sessions. Now we are going to start this session, and today speaker will be Dr. Harmanpreet Singh Kapoor, Department of Mathematics and Statistics, School of Basic and Applied Sciences, Central University of Punjab, India. He is gold medalist in MSc Statistics and won consolation prize in essay writing competition organized by Ministry of Statistics and Program Implementation, Government of India. He has published and presented research papers in reputed journals and international conferences. He is e-content writer and paper coordinator. His research interests involve actuarial statistics, risk models, survival analysis, financial mathematics, inferential statistics. I hope his experience really very helpful for all of you. Now I would like to invite today's speaker, Dr. Harmanpreet Singh Kapoor. Welcome, dear professor, in this session. Now I would like to permit you unmute. Dear professor, now you can unmute, and also it is request to all the participants. If you have any kind of question or query from your side, only then you should unmute. Otherwise, you remain muted during the session. Thank you all of you and welcome, dear professor, in this session.
Thank you, Dr. Merchant, for giving me this opportunity to share my experience with all the participants. So today I'm going to discuss about distributions and its application part. So let me start with my topic. I think all of you can see my slide. Is it visible to all of you?
Yes, sir, it is visible.
Okay. So let me, before discussing this topic, distribution and its application, so we all of you know that probability plays very important role in our general life also. So when we talk about probability, our main objective is to find out what will happen in the future with some, you can say, value, and we want to see that whether today it will rain today or not. So we assign some numbers to those things, right? So when we study probability theory and distribution, both are related to each other. So I am only focusing upon distribution part because nowadays our main objective is not to just find out the distribution for a you can say to solve real life problem, but also our main objective is to see how we can model or fit different distributions on the real life data set. So first I will, because in today's gathering, I assume that most of students are not aware about the distributions, and maybe some of them are already aware about the distribution. But I will start discussing with very basics of distribution, then I will increase the difficulty level with step by step. Okay. So as already discussed with you that in probability theory, our main objective is to find out the probability, and for that what we consider that number of favorable outcomes in the numerator part and the total outcome the denominator part. And this approach of probability was called classical approach. And after that we have another approach that is called frequency based approach to find out the probability, in which what we consider number of elements in the numerator and number of elements in denominator, and we assume that using that approach we can also find out a probability if that number of elements can be goes to infinite, right? So that was a frequency based approach, and after that we already have an approach that was called axiomatic based approach, in which if our you can say if some conditions or axioms are satisfied, then we are able to find out the probability. So
Excuse me,
basically
Professor.
distribution. Hello.
Please excuse me.
Yes.
Your PPT is stable.
I'm not showing anything.
Okay.
I was just discussing the
Okay.
the
Okay.
basic
Okay,
behind
sir.
it,
Okay. Okay,
why
sir.
I have chosen this topic. So
Okay.
I will
Okay.
come to that thing later. So basically, I'm trying to build up a frame that why I have discussed this thing.
Okay, sir. Okay. Okay. Thank
Okay,
you.
okay. So the thing is that when we talk about this distribution or this distribution and theory and its application, so basically we assign that we have a random variable. So I will come to the definition of random variable. Before that, I want to discuss about that why distributions are very important. So it happens that we have certain situation in which we conduct an experiment, we have a sample space, we have events. So it is not possible for each and every person to find out the probability in that prospect. So what we usually do, we assign a function over the samples events, or you can say event space, to the real number. So in that case, we use random variables. So in distribution theory, we first have a random variable, and after you can say we construct a function over the random variable that satisfies some properties. We will discuss about them. So there are some very random variables whose distributions name are not you can say they are not assigned specific names to them. So I am discussing here only those distributions that are very well known. So let's start discussing with the first thing, that is called what is random variable. So as already discussed with you, that while doing any, you can say, while conducting an experiment, so let us suppose we got some events, right? So this is my sample space and we have some events there. So it is also possible that let us suppose we take an example of a coin. So we consider that head and tail, there are two events only. Okay, so there are few experiments in which we have our you can say event space that is broader than the sample space event. So for example, if I want to conduct an experiment in which I'm interested to find out I'm interested to find out the probability that I will repeat the experiment till the time I will get uh, two times of head or three times of head. So this sample space will not work in that case. So I have to construct a new sample space, and that sample space will be different from this sample space, and that sample space is called event space, because based upon the events, based upon my objective, I have constructed a new sample space. And what I usually do, I assign the sample space events to the real number. So for that we use a term that is called random variable. So the definition of random variable says the quality or quantity that varies or may vary. So here this definition was from Webster dictionary, that says the equality or quantity that varies or may vary, because when we say that, when we assign a random variable, when we use a notation capital X for random variable, so it takes either a discrete value, discrete means integer based value, or continuous value. So when I'm assuming that it takes value of positive integer, so it starts from 0 up 0 1 2 and so on. Okay, and it can goes up to infinity, or it can be up to a specific value, right? Or when I am assuming that x belongs to a continuous variable, so I am assuming that it can takes value minus infinity to infinity in a close in interval. So it is also possible that when we have a finite value, then we can consider a closed interval here, right? So a quality or quantity that varies or may vary. Because why I'm saying that it is, or because you can see that x is not is rigid all of time. It can takes value 0 1 2 and so on. So it varies with time. Okay, or it varies with the, you can say, outcome of an experiment, right? So here y is equal to f of x. So here we have two variables x and y, and they are not constant. So x has some value. So you can see that, so there is a function that is defined over x and the outcome is coming in the terms of y. So we have some values of x, and you can see that the value of y comes up after putting the value of x in this function. Suppose x is something we do not know, but might take on a value due to chance. So what here you can see, so suppose x is something we do not know, but might take on a value due to chance. For example, so when basically we are mapping the sample events to the real number, or you can say natural number, or positive integers. So we do not know that what will be the possible outcome of conducting an experiment of tossing a coin out or throwing a dice. So suppose x is something we do not know, but might take on a value due to chance. So it means, but we know that, but in a dice we have 6 faces, in a coin we have 2 faces, or you can say the probability of getting heads while tossing a coin is half, or you can say while throwing a dice, the possibility of getting 1, 2, 3 or 6 face is has probability 1 upon 6. So because based upon the total outcome, we can assign a specific number to them, right? So x can be you can say the outcome of rolling a dice, or the result is random, right? So a random variable is to describe the possible values that can occur and the probability of those values occurring. So here as already explained to you, that while tossing a coin we can assign the probability half to them, and while throwing a dice we can assign probability 1 by 6. And we can use this you can say concept of, or examples to another you can say real life problems like auto insurance, value accidental or not. So here we can assign the case, or you can say we can assume that what will the probability that a claim will appear to the insurance company that has probability 1% or 99%. So it means when we have different types of you can say uh, situations, so the probability of happening of that situation is different, and vary from one situation to another situation, and based upon that we can assign random variable upon those sample events, and we can assign them random number correspondingly. So in this case we have basically two categories of random variable. One is called discrete random variable, and second is called continuous random variable. So in the discrete random variable, when a random variable take on value only from a finite or countable infinite sequence. So countable infinite means that we starts from 0, 1, 2 and up to infinity. Okay, so it is called countable infinite sequence, right? So continuous random variable, it means we can assume numerical values that variable x or y can take in a specific interval. That means if I am assuming that x can take value belongs from at x belongs to in this interval 0 to 1, so it means I'm saying that x can take any value that lies in this interval. If I'm taking a specifically closed interval, so it means I'm also saying that it also takes value 0 as well as 1, right? So continuous interval can assume numerical values from an interval of real number, or perhaps the whole set of real numbers. So here, when we talk about discrete random variables, so we have a function, either use a notation p of x or f of x, and most of the books use this notation PMF, that is probability mass function for discrete random variable. Okay, so random variable has two component or values of probability. So the things are that it can be assigned by notation p of x or f of x, and usually it can be represented in this way: probability of x is equal to x, because we can find out probability for a specific point in this discrete random variable, in the distribution of discrete random variable, and our this probability mass function satisfy this condition that it lies between 0 to 1, or it can takes value f of x value will be 0 or 1 for specific cases of when we have no events, and when we have whole sample space, then the probability of f of x is the value of f of x is equal to 1. And the second thing is that when you integrate over the possible values of the probability mass function, its value should be equal to 1. Okay. Similarly, we have few properties for the continuous random variable. The few property says that when we integrate over this when we integrate the PDF of uh, x variable over its range, then that values should be equal to 1. And in the same way that the probability mass function has value lies between 0 to 1, similarly for the PDF, it also lies between 0 to 1. Now there is a very important property that continuous variable holds. The property says that if someone wants to find out a probability for a discrete for a continuous random variable for a specific value, so the value is equal to 1. The reason is that in continuous distribution, we are not able to find out a probability for a single point. We are always finding the probability that, let us suppose this is the area under the curve, and we want to find out the probability for this interval. You can easily find it out, but one cannot find out a probability for this line only, right? Or you can say corresponding to this point one can find it out. So that's why when someone has observed that when someone want to find out the probability for a continuous variable for a specific point, that will be always 0. Okay, so I am going to discuss a very simple example here. So we have a variable x, okay, and the function for the variable x is defined as f of x is equal to 2x. So so if we want to cross check whether it is a probability density function or not, so one can easily verify that by by integrating over its range. So if the probability is coming out to be 1, then we can say that this is a probability density function. So for that, for that what one has to do is one has to take integration over its range, because we know that the lower limit is 0 and the upper limit is 1. So when someone integrates from 0 to 1, and 2 of x is the probability density function, and when we integrate over this range of x, then if it is coming to be 1, then we can say that this is the probability density function. And also you can see, so when we put any value of x in this function, so the f of x always lies between 0 to 1. So it means it satisfies these two criteria. The first criteria is that the probability density function lies between 0 to 1, and the second criteria is that if we integrate over this range, or the PDF is integrated over this range, then the value is coming up to 1, then we can say that this is the probability density function. Okay, so another property of this random variable is that cumulative density function, or one can easily see the lot of expressions are used. Either one can use f of x, either one can use probability of x is less than or equal to x. So here you can see that the expression is defined as that if we are talking about for discrete for a continuous setup, then this f of x is defined as minus infinity to x f of x d of x. So here, so if we have a upper limit different from minus infinity, one can start from that limit and goes up to a particular value of x, then one can easily find out the cumulative density function. So for what is cumulative density function, let me help you to understand this. So here in the previous case, let us we already have derived the probability of f of x. So f of x is basically a probability that one has observed for a particular interval. So, but if someone wants to find out the probability till a particular point of x, starting from minus infinity till a particular point of x, then one has to accumulate all the previous probabilities. So one can say, starting from this minus infinity to till this point, let us suppose this is 10. So first one include or accumulate the probabilities that someone has achieved till this point minus infinity to 10, then minus 10 to this 20 and so on. So when we keep adding the probabilities of different intervals, then one can get the cumulative distribution function. Okay, and there is a opposite you can say that expression of cumulative density function, that is called survival function. So here x of x is equal to 1 minus f of x. So what does it mean? So in reliability theory or in survival analysis, this concept of CDF and the survival function are very important. The reason is that because the CDF are basically used to find out the probability that at what time period, what is the probability that at what time period a component survive or component works, or the what is the probability that till a particular time period component fails or not. So if someone wants to see that what is the probability that let us suppose I am taking example here. Let X respond the working lifetime of a bulb, let us suppose. So if someone wants to find out a probability that, what is the probability that the bulb lights for 1000 hours. So if someone wants to find out this probability, this is the case of CDF. Okay, because I am putting a specific value of X and one can find out this probability, and then one can easily see that based upon this probability one can make an assumption that this bulb's lights up for 1000 hours or not. Okay, and opposite of that is survival function. So you can see that this relationship is opposite. That shows that what is the probability that a bulb that survive for at least, or you can say the bulb lights for at least 1000 hours. So what is the probability of that? So whatever the probability that you will achieve in this point, that is the opposite of that you will get here. So this way, this concept of cumulative density function and survival function, they are very important in different areas. So I am just giving one example here.
What time?
Okay, so now I'm going to discuss about few discrete distribution. They are very important in literature and they're widely used. So I'm just I'm just started my presentation with the basics concept, and I'm trying to incorporate more difficulty level with step by step. So try to be with this, be with me during this session. So here, so we assume that, or you can say, in generally we have read a lot of time that what is the probability that when when we you can say toss a coin. So we generally say that half is the probability of conducting, half is the probability of getting head, and half is the probability of getting tail. Okay, so to assign a function, so or you can say one can easily see that. So in distribution theory, so generally this Bernoulli distribution is assigned to find out a probability when we have only two outcomes. So I will discuss with you. Then we have binomial distribution. So I will also show that binomial distribution is a generalization of Bernoulli distribution, or one can see that Bernoulli distribution is a special case of binomial distribution. Then we have, when we will discuss about a different distribution that has different characteristics as compared to this Bernoulli binomial, and then we will discuss about negative geometric distribution, and after that we will discuss about a very important distribution is discrete setup, that is called Poisson distribution. So as already discussed with you, that certain probability distribution occur with such regularity in real life application, and they have their own names. So basically, when we have a specific form of PDF, okay, and those PDFs are named upon the, or either they are named upon the very you can say famous statistician or mathematicians, or they have certain characteristics, and if someone find that your data set follows this particular distribution, then one can use those properties. Like what are the properties? Is because we know that Bernoulli if the data set follow Bernoulli distribution or binomial distribution, so we already have the expression for the mean, variance, and standard deviation, and based upon that one can understand the characteristics of those data set, or one can use those results of the Bernoulli or binomial distribution on the data set, so that one can inference more, or one can get more information about a particular objective. So here, let me start this Bernoulli distribution. So as already discussed with you, when any random variable takes only two possible values, 0 and 1, so we have certain assumption here. The assumption is that the probability that this experiment, while conducting an experiment, the situation is normal. Okay, and here we are saying that this random variable can take only two possible values, one is 0 and 1. And why we are saying that this is discrete random variable? Because it takes only two possible values, 0 and 1, and the probability density function is defined as pi of x, 1 minus pi, 1 minus x. So this is a function that already satisfies the conditions that I already discussed. Okay, that the probability density, this probability mass function lies between 0 to 1. When you integrate, when you take summation over all the possible values of x, then its value should be come to 1. So here pi, this pi x notation, that takes value 0 to 1. Okay, So it means now I'm trying to correlate this situation with this very simple example of tossing a coin, in which we assume that what is the probability that while conducting a coin we get head or tail. So if I assign pi is equal to half, then you can see that here, if I'm interested to find out the probability of getting head, so if I am assigning x is equal to 1, because if I'm interested to find the probability that x the coin is the output of the coin is coming to be head, so I'm assigning x is equal to 1 as my desired outcome. So I'm taking x is equal to 1 here. So pi that takes value half, because I'm assuming that probability of getting head is half. So the power of this x, this half is 1, and 1 minus half power is 0. So you can see that the final answer is coming as half. So either your objective is to find out the probability of getting tail, but in the same case, in this case you are also assuming that pi is half, so you will get the same answer. But if you assume that pi is less than or greater than half, so and you are interested to find the probability of getting head while tossing a coin, or getting tail while tossing a coin, so the probability varies. Okay, so it means that whatever the probability that you assume here, you will get the same answer here. But here you are saying that, but why it is important to study this distribution? The reason is that because we know that the mean of this variable x is p, and the variance of this variable is pq. And based upon that, because we have results with us in the literature, and using those results use one can directly use this result and come up the conclusion. So this is the main idea, that why we are discussing this distribution. The reason was that we know that this, let us suppose we have some data set, and while fitting a particular type of data set, we got an answer that this data set was fitted by a particular distribution, right? So we directly use those characteristics of those distribution and apply those characteristics while getting an inference. Okay. So the second distribution that is widely used is called binomial distribution. So there are few scenarios one can use this binomial distribution. The first scenario is that the number of heads or tails in a sequence of coin flips. So now you can see that in the binomial distribution, we are interested about the number of heads or tails. So this is similar with the distribution that we just discussed, that is Bernoulli distribution. The difference is that in the Bernoulli distribution we are conducting only a single trial, but in the binomial distribution we are not conducting a single experiment or single trial. We repeat the trials with some assumption. The assumptions are that the trials are independent, the probability remains same, and we are interested to find out the total number of heads or tail in a sequence of coin flips. And we can also use this binomial distribution to count to vote counts for two different candidates in an election. So now you can see, so there are two candidates, but because we are doing the vote counting, and vote countings appears from different candidates. Okay, so there are candidates who vote for person A, there are candidates who vote for person B. So if you can say note count the nodes or count their vote counts, so we are not conducting a single trial, we are repeating an experiment, and we are assuming that vote count of one candidate is different from the vote count of different candidates, and the probability remains same. Okay, the third is the number of male and female employees in a company. So now you can also see that when we talk about the number of male and female employees, so there are only two outcomes, either the employee is male or female. And in a company there are not a single employee, there are a lot of employees. Okay, so one can use this concept again in this example also. The next example says the number of accounts that are in compliance or not in compliance with an accounting procedure. So it means here you can see that there are two possible there are two outcomes. One is account is compliance, or no account is not uh, compliance, but we do not have a single accounting procedure, right? So we have multiple number of times of you can say accounting procedure. So that's why we are counting the number of accounts, right? So the number of successful sales calls, because the outcome can be not successful or successful. So if we are only interested number of successful sales, so that will be can also be modeled through binomial distribution. And similarly, the number of defective products in a production run. In a production run, there are products who those are defective or non-defective. So if we are interested to find out the probability that how many defective products are there. Okay, so from the whole lot where there is not only one single item, there are it may be 1000 items in total or 1 lakh item in total. So this binomial distribution play a very important role in that case to find out the probability of number of defective items, the number of days in a month, and your company computer network experience a problem. So because we have number of days, and our main objective is to find out that whether you experience a problem or not. So the possible outcome can be whether experience a problem or not experience a problem, and we are counting for each day. So whether the computer network experience a problem or not. So this can be also modeled through binomial distribution. All these case are comes under discrete setup. That's why we use this binomial distribution, and there are few assumptions that one has to keep in mind while fitting this binomial distribution over the situation. The first assumption is that a set of n experiments or trial are conducted. So here you can see that all these examples, like flipping a getting head or tail in a sequence of coin flips. So n is not equal to 1, n is greater than 1. So vote counts for different candidates. Here also we have n, or you can say we have more than one trials or experiment. And in the same case, in all these case, we have n experiments, and each trial could result in either a success or failure. So as already discussed with you, that in each case we have only two possible outcomes. Either we are getting head or tail, either we are getting votes for in favor of one candidate and in favor of second candidate. And here the number of employees either are female or male, and the number of accounts that are in compliance or not in compliance, and number of sales call that they're successful or not, and whether the products are defective or non-defective. Okay, the number of days. The number of days in a month your company computer network experience a problem or not. So these are two you can say outcomes. So the probability P of success in the same for all tries. So here we are talking about that probability P. So when we conduct a one trial, the probability, what are the probability that you assume that remain constant while conducting a second trial or while repeating the same trial for other time. Okay. So the outcome of different trials are independent, as already discussed at the starting point, that we are assuming that when we flip a coin second time, third time, they are independent from the second time or the first time. And in the same manner, when we vote, when we do the vote counting, so we are assuming that vote in the favor of that the first candidate vote for the candidate A, that is different from the vote that other candidate given to any other candidate, either given to candidate A or B. So they are independent. So in the same way, so when we're talking about number of employees in a company, so if some of the positions are given to male or female, so while doing this study, we are assuming that each position is given to male or female independently. Okay. In the same manner, when we talk about the number of getting success in calls, that is so number of getting success in each call, that is independent, right? So here, so we assume that x, that is a random variable that is used to count the total number of successes, right? So in this n trials, okay, we whatever success we get, we assign, we you can say we use this capital X notation to count this number of successes, and this X variable that follow binomial distribution. The probability density function of binomial distribution is this one. So here, so you can see that this form of the binomial distribution is similar with this Bernoulli distribution if you put the value of n is equal to 1. Okay, for example, so here when we put n is equal to 1, so here it will be 1 factorial and x factorial 1 minus x factorial, and here x can takes only value 0 to 1. Okay, in the case of Bernoulli distribution I'm talking about. So here you can see that, so the final answer will be p of x 1 minus p 1 minus x. Okay, because x can takes only value 0 to 1. So here the final PDF of when we put n is equal to 1, we will get this final form. Okay, so the reason is that why we have incorporated this constant term with this form of the PDF. The reason is that because here you can see that this is just notation of NCX, right? So it means we are interested to find out the probability that total from total n tries, what is the probability what is how many combinations?
Allah bani Earpiece. Earpiece. Yana nan cikin mutum. Mutum nake yi zan ɗan.
There are few background noises. Either you mute yourself or either continue. Okay, so NCX means that we are extracting X possible X favorable outcome from this total outcomes, right? So or n tries. So that's why we multiplying this NCX term with this concept of P of X 1 minus P n minus X. So this is basically a modified form, or you can say generalized form of this Bernoulli trials. So the difference is that in space of one trial, we are conducting n trials, and the probability remains same, and these trials are independent of each other. Okay, so here we have two parameters n and p. So one I already explained the concept to you. The probability of for observing any sequence of any independent trials, they contain x successes or n minus x failures. Okay, so that's why the p of this x represents the probability of success, and 1 minus p represents the probability of failure. And that because we have total outcomes, total possible combination, this is n, and we are selecting x, that's why we're using ncx and ncx this expression with this PDF notation. Okay, so there is one example that will help you to understand this concept. So we already, all of you are aware about the concept of multiple choice exam. So let us suppose we have taken 10 multiple choice question in which there are 4 possible outcomes, and we are assuming that these four possible choices have equal weightage. So that's why we can say that the probability of getting the success is 0.25, because how you will determine this? This is 1 upon 4. This 1 upon 4 is 0.25. So our main interest is to see that x be the number of questions the student answer correctly. So if x is a desired random variable, we want to see that that if student how the number of questions that is answered correctly by the students. So we can assume that total we have 10 questions, and the probability of getting success is 0.25. Okay, and we want to find out this probability, that probability of x is equal to 0. That means that this probability shows that the student is not able to answer any question correctly. So what is the probability for that? So we know that n is equal to 10. So we have a formula ncx. So we put the value of n is equal to 10, x is equal to 0, and we have the value of p is equal to 0.25. And after solving this, we will get this value 0.0563. So let me help you to that how one can derive the same probability using this MATLAB. Sorry. So in MATLAB, the beauty of this software is that you do not have to put this form of the PDF form of the binomial distribution and other distribution, because this form of the this PDF and CDF expressions are already inbuilt functions in MATLAB. You just have to know that which key term, or you can say which syntax you have to call to execute or to find out the PDF or CDF. So let us suppose in the question that I've just discussed with you. So I'm interested to find out the PDF for the binomial distribution when x is equal to 0. Okay, so I'm just start with this expression. So let me first discuss with you that what I have done here. So in this syntax, I have written x1 that is equal to PDF and bracket open, parenthesis open, or you can say, and inverted this single comma, inverted comma, binomial 2 comma 10 comma 0.25. Okay, so in the example, I have derived the probability that what is the probability that that student is not able to answer any of the 10 question correctly. So the syntax says, so the PDF is notation for the probability density function. When we and this is a parenthesis, it means I have to input my this keywords in this format. So the first this place is reserved for the distribution. So when I use this syntax or function PDF, okay, I first have to write down the name of the distribution for which I want to find out the PDF. Then after that, and this syntax is used to find out the PDF, and after that I want to find out the PDF for x is equal to 0. That's why I will put here 0 and comma, because I am segregating, or you can say separate this each element or each argument by comma here. So after that, I have to define the parameters. So we know that we have 10 questions with us. So that's why I'm putting 10 here. Then after that, putting comma. So we have the value of p is equal to 0.25. So I am putting 0.025. Now to execute this command, the shortcut is F9. Let me check. Okay, so you can see the answer is coming as 0.2816. Okay, not sorry. This is for the second. Okay, the answer is coming as 0.563. So this is the answer. Okay, here the shortcut is F of 9. But I am not able to execute this single line command, because if I execute this online platform Cisco, that command is executed for that one. Okay, so it means if I execute this, another function is working on at a simultaneously. So to execute this, either you can use f of 9, or either you can directly execute this command and you will get the answer. The answer is coming as 0.0563. So here you can see the answer is 0.0563. So you can easily see that how one can easily compute the PDF for the binomial distribution. Now coming next to the example. Now let us suppose you want to find out a probability, that what is the probability that if student get 2 right answer among these 10 questions. So you just have to put the value of x equal to in this expression of the PDF and then solve it further. But if you want to execute the same thing in MATLAB, you just have to replace 0 with 2, right? And when you execute it again, you can see the answer is now 0.2816. So you can cross check that this is the same answer that you're getting here. Okay. Now, as already discussed with you, that CDF is play very important role for any distribution. So here, if someone wants to find out the probability that what is the probability for the student to fail the test. So what does it mean? So the criteria is that, let us suppose that if student is not able to score student is not able to get more than 5 correct answer, then he will be failed, right? Or you can say if the student is failed if it has less than 6 correct answer, right? So you can see that to find out this probability, what we are doing now, we are finding out the cumulative density function, that means CDF. So the value is 5 now. So either you can solve this expression for start with solving this expression for x is equal to 0, 1, 2, 3, 4 up to 5, and then add those probabilities, right? And after solving this, you can see that the final answer is coming as 0.9803. So it means that the probability for is very high for the student to fail the test. Now how to solve the same thing in MATLAB? To you can see that I'm using a syntax in place of PDF. I'm using a syntax CDF here. So I'm using the same because I'm solving the probability for the same distribution. So I'm using the same syntax binomial distribution here. So here in place of 2, I'm replacing with 5, 5, right? And the parameters, the rest of the parameters are same. Clear? So when I execute this command, you can see that the answer is same that we got in the previous expression, right? So here in this way, the reason is that why I'm showing the code to you, that if someone wants to if your talk is very important, then you can share also with us. Okay. So the thing is that why I'm sharing the code to you. So let us suppose, so those students or those persons or those researchers who are not able to solve this derivation part, or they just want to use this distribution in their research or and other fields, right? So they can directly, if they are able to understand the logic that how this distribution is important in their area or topic, they can directly use the MATLAB to solve those problems, and they also save their times. Okay, there is not only just one software here, that is MATLAB, that can solve these problems. One can use another softwares like R and Python, but here I'm only focusing upon this software of MATLAB and also discussing with the code that how one can write down the code and solve those things. Clear? So now, as already discussed with you, that in the case of binomial distribution, we have this mean and variance form is given to us. Similarly, for the binomial distribution, there is for just further expansion of this form of mean and variance. So in the binomial distribution, we have mean as P and variance as PQ. So in the binomial distribution, we have mean as NP and variance as NPQ. So P, because there is a property that P always lies between 0 to 1, and there is another property that P plus Q is equal to 1. So one usually, most of times, either Q can be written as 1 minus P, or P can be written as 1 minus Q. Okay, so one can solve these things directly, and let us suppose, how one can find out this probability in the MATLAB. So for that, we have to use another syntax. So to solve the mean and standard deviation of variance, you first have to define, or you have to first define that we are talking about the binomial distribution. And for that, we have to use a command that is called make distribution. Using the make distribution, we first assigning, or you can say we are giving instructions to this MATLAB this compiler, that we are talking about the binomial distribution, and in which the n has value 10 and p has value 0.25. So when I execute this command whole together, and in this PD, this binomial distribution with these parameters is stored, or you can say the complete PDF is stored under this variable PD, then I evaluate when I execute this command mean and standard deviation, then it derives the mean and standard deviation for this distribution. So I have already executed this result. So let me show it to you. So here, when I execute this command PD only, using this syntax, this function make distribution. So it means, but so I am constructing a distribution of binomial because I'm using a syntax of binomial with n is equal to 10 and p is equal to 0.25. So here you can see that. So while executing this command, you can see the value of n is equal to 10 and p is equal to 0.25 and m1, because here in m1 I'm storing the value of mean of the PD, that is binomial distribution. So it is coming as 250, and when here so it is very easy to find out the standard deviation, okay, in this MATLAB, because standard deviation is most widely used. So we know that there's a relationship between standard deviation and variance. So if someone has find out a standard deviation, one can take the of that will give you the variance. So I have find the syntax of standard deviation because I do not want to repeat the same thing again. So I'm using standard deviation here. I can also use another expression to find out the variance directly. So here you can see that the answer is coming as 1.870. So let me match this concept here. So here both the answer are coming to be same. So here you can see that how one can find out the mean and variance for this binomial distribution, and you can repeat the same thing for other distribution, other distribution also, like geometric distribution and other distribution that I will cover now. The main idea is that how one can find out the probability. Okay, so I have just explained, I have taken few example for these two distributions for binomial here, and when you put n in place of 10, if you put 1 here, you will get the answer of the binomial distribution. Okay, let me come to the my topic of now. Till this point, what we have covered Bernoulli and binomial distribution. I also have discussed that how these two distributions are related to each other. Now I'm going to start a new distribution, discussing a new distribution that is called geometric distribution, and the concept of geometric distribution is entirely different from the binomial distribution. So in the binomial distribution, we are only interested to count the number of uh, you can say interested events or number of favorable events in which we are interested. Let us suppose in the binomial I have discussed with you that in these examples I'm only interested to find out or to count the number of heads or tails while flipping a coin in a sequence and so on. So in the geometric distribution, my interest is that what is the probability that uh, what is the probability of getting a one success, or that for that I have to repeat
These are on hard.
multiple number of trials, or you can say I have to conduct multiple number of experiments. For example, let us suppose a patient is waiting for a suitable matching kidney donor for a transplant. So you can see, so there is a situation in which a patient is waiting for a suitable matching kidney donor for a transplant. So the probability that a randomly selected donor is suitable match is 0.1. So what does it mean? It means that so there are different donors. Okay. So but a patient has you can say a different situation in which he's waiting for a suitable donor, and the probability of getting a suitable donor is 0.1. Okay, so it means that so there is a donor who offers his kidney to a patient, so it is possible that donor kidney matches to the requirement of the patient kidney. Okay, it is possible or not. So it means, so we conducting a trial, so this is an experiment, and in which it is a possibility that you will get the success at the first trial, and it is also possible that you will not get success at the first trial, right? So when we did not get the success at the first trial, so we move to the second one. So it means we are moving to the second donor, right? So again, it happens that you will get a success. That it means you will get a suitable donor for the patient or not. So what is the probability that you or you can say what is the probability that you will get the first success? Okay, so in that case we use geometric distribution. So it means we are not concerned about that how many trials or experiment we conduct. We are only interested to find the probability of getting first success. Okay, for that we have to, it may possible that we will get success at the 10th trial, we will get success at the 50th trial, and so on. Okay, so continuing in this manner,
Only run. Yes, open.
the probability mass function for the geometric distribution is probability of x is equal to x, 1 minus pi of x is equal to x, right? Oh, sorry, 1 minus pi power x into pi. So in the Bernoulli distribution, the form of this probability mass function was pi of x 1 minus pi 1 minus x. So here we have opposite relationship. So somewhat is like opposite. So we have 1 minus pi power x and into pi. So it means we conducted, you can say, x trials, and after that we will get our first success, right? So this parameter pi takes value lies between 0 to 1, and that shows the probability of getting first success, right? The parameter pi can assume values between 0 to 1, and depending on what parameter pi is, we get different members of the geometric distribution. So generally we use this notation x follow g at pi to indicate that x is a geometric distributed random variable. The concept is same as I already discussed with you, that in this geometric distribution our main interest is to find out the probability, that probability of getting first success. For that we have, it may possible that you will get success in the first trial, or you have to repeat the same experiment till the time you will get the first success. So it means it can be 1, 2, and so on, or 0. It starts from 0, 1 to so on, because we have defined this probability density function in this manner. So if x is equal to -1 here, okay, so it starts from 1. Okay, so another distribution that is most widely used, that is called negative binomial distribution. So here you can see that, so in the negative binomial distribution, we are not interested about the first success, we are interested about the RS success. So it means, so let us suppose, so if we extend the same situation to 2 patients, okay, so in spite of 1 patient we have 2 patients, so we will search for the donors, or we will search for the donors till the time we will get 2 such suitable donors whose kidney is suitable for 2 patients. So it means, so in spite of 1 patient we have 2 patients now. So if we repeat the same experiment till the time we will get 2 patients, suitable patients. So this is the case of negative binomial distribution. So here so the notation for the negative binomial distribution is x follow negative binomial distribution with this format r comma pi. So r, if r is equal to 1, then this negative binomial distribution will become geometric distribution, and they have the similarity of this characteristic similar with this binomial distribution. So now I'm coming to the another distribution that is very important, that is called Poisson distribution. The Poisson distribution is basically derived from binomial distribution, and the criteria is that when we have infinite trials, and the probability of getting success is very small. So it means, so when we assume that n is equal to n approaches to infinity, and probability this probability of getting success approaches to 0, so n of p can be approximated, or you can say this, there is a approximation result that binomial distribution can be approximated by the Poisson distribution. So I will come to discuss about this. So let's, if Dr. Meher, are you there? Hello.
Sir,
So should we stop here for 15 minutes break, or should I continue?
yes, we can take a break for 15 minutes. Dear participant, there is a break for 15 minutes and it's 1:30. And after 15 minutes means 1:45, we will resume the meeting again. So there is a small break and you can enjoy a cup of tea.
So there is a request that you should keep your mic mute, right? Because there was lot of disturbance, and I not able to communicate properly.
Okay, sir. Okay.